Finally, it's working. Great. Yeah. So today, I guess I'm mostly going to talk about this paper we wrote last year. This is that I cleared this year as an oral, but I guess it's some content from this paper, but generally this theme of scaling reinforcement learning for LLMs. And if you are active online or if you've been seeing what's happening in the LLM land, this is actually in the Zeitgeist almost, or was in the Zeitgeist for last year, and maybe even this year, that you hear this thing scaling RL quite a bit, but no one really knows or no one really explains what they're talking about and what are they really saying when they say scaling RL, because it means so many things. So the hope is that after this lecture, you have some understanding and maybe even like some technical details of how do we even actually measure this, characterize this, think about it, and what can we do better. So there are certain things I'll talk about, but the hope is after this, you should be able to think maybe better ways of scaling RL, or where is it going, or what does it mean to do scale RL, and stuff like that. All right. So I guess it's fair to say that, okay, one more thing, by the way, feel free to ask me or interrupt me for questions or discussions in between. Otherwise, this will be a quicker lecture because I don't have as many slides. So yeah, feel free to stop me whenever you're confused. It may be a thing I haven't explained well, or if you have some questions or follow-ups to ask. So that's totally okay with me. So yeah, so I think what I was saying is it's totally fair to say that the reinforcement learning training is like the new scaling frontier for large language models. You can think of pre-training as something that teaches a model or a language model about the world, which is you train on all the tokens out there on the internet, and you learn the distribution of, oh, if there was some random sentence someone would say on the internet, what would be the next tokens or next text coming out of after that random sentence. But it is reinforcement learning that unlocks the capability that we really use or that matters the most. For example, things like test time thinking, which is you have, I don't know if you're interacting with these chatbots like OpenAI's models or Gemini or whatnot, and they can think a lot before giving you an answer, or these agentic capabilities. I'm sure a lot of us are using things like Cursor or Claude Code or whatnot, or even things like scientific discovery, which is basically you want these models to be able to find unknown things which might not even exist and we don't know if they exist, but we can make an attempt at those things. And reinforcement learning would be at the forefront of all these capabilities or things that we really want to do. And just to give you some more context, you might have seen these plots or images quite a lot, but again, it doesn't hurt putting them in context again. So the left plot is showing here is about test time reasoning, which is, I think OpenAI released this blog post maybe a couple of years ago where they showed that as you increase the amount of compute the model have at train time or test time, the performance on this, I think, high school competition math problems increases. So and this is like the compute here means train time compute here means RL compute, or that's what we can assume. That basically as we are scaling reinforcement learning compute, the model's performance keep improving. And the compute is usually on a log scale, and you're seeing, I guess, accuracy of the model. Similarly, another plot I'll share is from the Cursor folks, where they are showing like the agentic capabilities or the coding capabilities of the Cursor agent that we use for in our day-to-day lives keeps improving as I increase the amount of training compute. Again, you see the log scale of the training compute. So this is the amount of reinforcement learning training compute. Again, think of this as like how much compute or GPU hours I'm spending for my reinforcement learning training. That is that the x-axis is. And the y-axis is showing as I do more of it, things just generally improve. This is what I want to show from this plot. And yeah, so left, you can think of it as reasoning or thinking capabilities, right? You can think of that as software engineering abilities. And these are like some really valuable things that we want out of our models. All right. And the other thing which you can note based on just like the kind of plots these frontier labs put out is the amount of RL compute is exploding. So on the left, I'm showing a plot on OpenAI 01 versus 03. These models were, I think, 4 months apart, but the amount of compute scaling is 10x. So 01 was at some amount of compute. If you scale RL compute by 10 times more, you get this 03 model, and you can still see that there is a pretty substantial increase in performance on this benchmark. You're almost nearly solving it at this point. Similarly, if you look at these models from XAI, they are also showing that from Grok 3 to Grok 4, the amount of increase in RL compute was 10x. So you can see that we are substantially increasing the amount of compute we are spending in RL training for these models. And I guess when Owen was released, let's say a couple of years ago, maybe this picture made a lot of sense to people. People might have seen like this famous cake picture from Jan LeCun that we used to call it cherry on the cake. And the argument is simple. So think about bits of information from each kind of training that gives you. So he's saying that basically supervised learning is like the icing on the cake. Self-supervised learning is the cake or cake genoa. And the reinforcement learning is the small cherry on the cake, basically. And you can sort of map this picture to our language models too, at least a couple of years ago, right? Which is if the amount of compute we spend in pre-training was train on all of internet, and we do this really large and expensive run and train really huge models, if that's the bigger circle, then RL compute, again, this is directionally correct. I don't know the exact sizes. This is from this slide from someone from OpenAI. But you can imagine that this cherry on cake picture might have been true a couple of years back, where the RL compute was the small cherry on this big cake of pre-training compute. Now, it's possible that we are flipping this picture now, or we are heading towards a direction where we are flipping basically, and again, this is just extrapolation from this slide. This is when is this plot from? This is from, I think, last year. And now this is 1 year later that, and we're still scaling RL. So imagine the amount of compute increase in RL and whatnot. So basically, the cherry got bigger from 01 to 03 is how you should think about it. And then what I'm saying is, this is like maybe not so hard to imagine either. That if we just keep doing or keep going along the path that we are on right now, maybe we'll have like a very tiny cake and then basically very big cherry, or the cherry is the entire cake. The other way to think about it is it's like, what is the paradigm difference? So pre-training was about learning from the tokens or the text on the internet, and that's great. Reinforcement learning is about learning from experience or learning from our own interactions with some environment. And this is what we do all the time. You are learning from the environment, where the environment includes me at this point, and you're learning from me, and you're listening to this, you're thinking about something, and blah, blah, blah. This is not something as if this is an internet token. Like you chose to attend this lecture. If you didn't do that, you wouldn't be learning this thing at all. So in a sense that it makes sense, right? Like we want our language models or models to be able to do things that we are really good at. And we just want them to place in environments which enable them to learn this. And reinforcement learning is that paradigm. So it looks crazy as a picture, but maybe it's not that far off from what reality, one possible reality that could look like. All right. And now I think at the same time, scaling RL is more art than science. Like I showed you all these plots of how much RL compute is increasing, like 10x saying, everyone saying that, making these plots like, or saying things like ludicrous rate of progress, and you can look at that plot saying, oh, the bars of pre-training and RL look same. No one knows if that's true, but they're just showing how much RL compute is scaling. But as I was saying earlier, we really don't know how do we actually scale RL. Like we hear about this thing all the time that RL compute is increasing and people are scaling and whatnot. And what do I mean by that is there's not really a scaling framework we have access to. For example, if I asked you that, hey, if I were to scale the amount of compute for this method 10x or 100x, can you tell me if this is going to keep scaling this way? Or what is the form of the scaling? Like, can you even predict? So basically, if I give you 10 things and I say, oh, this works better than this method at this compute scale. Now, if I were to 10x the compute, can you still say something about the ranking of these things? And this is a basic question, right? If I'm spending $1 million in this thing now, and let's say now I want to spend $100 million, I really would like to know, is this $100 million is going to be a good use of this compute, or should I do something else? And that is what I meant by we don't have any scaling framework. Similarly, there are a lot of ad hoc solutions. Pick any report from frontier models that do release these technical reports. Like, I guess I've given some examples from QuentFolks, Minimatch, this like a long list. Everyone's RL stack would look very different. The recipe would look very different. So these are all very ad hoc solutions that they designed for their custom stack, and it worked for them. But then if you switch the report to, let's say, DeepSeek or someone, then it look very different, and then so on and so forth. So there's no like unified view of what actually scales versus what doesn't. All of these basically solutions work for them at a specific in a specific context, but we don't know. If you were to try that solution now, would that work for you? I don't know. It worked for them. They are not saying that it will work for you. And finally, I guess this also excludes a lot of communities which do not have the same amount of compute. which is if to basically understand RL scaling, you have to scale it. Meaning, if I want to spend $100 million for RL scaling, and to understand what happens, do I really have to spend $100 million? So if that is true, only some players can do this. Meaning, let's say only the big labs, which have this much amount of money, can study RL scaling, while the others just cannot even think about this because they don't have any made. So we really want some way to predict that if I want to scale RL compute, what would happen? Because if we don't have a way like that, then basically we are excluding a big community from even thinking about this research, which is like the reason we should even consider like why basically think about making it a science rather than leaving it as an art. So far so good. Any questions so far? Yeah.
So do you think there will be a data bottleneck? Because obviously LLMs are built on it's more like stripping the entire internet, and the oral component is often like for a downstream task.
Sure.
But do you expect that you'll have a problem where you'll reach a point where it's hard to scale up more because you're kind of lacking sufficient data to do so?
Oh, you're saying we will run out of tasks? Is that a good rephrasing of the question? Yeah, that's a great question. I think getting very useful tasks is not as easy as just scraping the internet. Because let's say tasks are a different kind. For example, think about your software engineering tasks. There was a GitHub and there were pull requests and whatnot, and people were able to make use of that. But let's say one thing I mentioned, and this is like something I work on. We want to work on, let's say, I don't know, task of discovering new superconductors. That is something that I do as like where I work at. And this is not an easy task to set up, right? We actually had to set up an autonomous lab so that we can make new materials and we can try it out. So basically, setting environments is not an easy feat. Like it's not as easily available as the internet. That's it. We definitely have a huge long list of environments that we would want our agents to do. For example, you would wish that most of the things you're doing on a computer, rather than you doing it, hopefully maybe your agent can just do that. And if your agent is not so good, or the LLM is not so good at that task, maybe you can just set up an environment with that thing and train your model on it. Now, I'm not talking about how costly is this, or is this even feasible? Like we are saying there is a possibility that this can be done, and that is let's think about any valuable domain, which actually has a lot of value, like coding was one of them. Now we are seeing our models are getting more and more capable. Similarly, think of any task which has a lot of high value. I do think we'll start training on those tasks too. And now there is concerns about how easy or hard would be to train on these tasks. So some tasks might finish in minutes, like solving math problems, while some tasks might take hours. Like for example, one task could be writing research papers. This is not an easy task to train on, and not an easy task that they quickly get a signal on, but it's still a task that people might start setting up and whatnot. So to answer your question, I think there will be enough interesting tasks. It's just that the difficulty of setting these interesting tasks might keep increasing or may not be as easy as just scraping the internet. All right. Yeah.
Do you think like is compute the real bottleneck? The thing that seems to me like in the pre-training era, like it used to be the case like compute is one of the bottlenecks. And now we are at a stage where we are saying your data is limited. So at this point, compute is no longer bottleneck. But for RL, it seems to me the biggest bottleneck is really the environments, right? The feedback coming from the environment. Even if you have a lot of compute, it's really not so useful because the delay of getting the feedback is much longer.
This is great. I think so. RL has definitely both the bottlenecks. So there is the bottleneck of what kind of environments I should train on, and then there's the question of I know these are the best environments I should be training on, and I have some amount of compute. Let's say I don't know $100 million to spend. What is the best way to use that compute? So I think this talk is mostly about the second question. There is a separate discussion to be had about, I guess, what are the best environments to train on? What is the best way to set up these things so that we actually are set up for success and whatnot? That is not what I'm discussing, but yeah, that is a very valid thing that we should separate these two questions. Like both, and I think this is related to the task thing someone asked before, which is coming up with interesting RL tasks, and so that they are learnable and LLMs make progress on them is itself an interesting problem. And then assume we have these set of tasks that we have already come up with. And now we are saying, I have this much compute, because we do have a lot of compute and more compute is coming up. How can we actually use that compute? And I think this is thinking about that question of assume fixed tasks and think about, I want to scale compute. What do I do with this? All right, I'll move on. So I guess maybe this slide kind of preempts the question which I was asking, or what the focus of the slide is. So I guess, why do you even care about this kind of predictable scaling business? Like, why do you even care about predicting if I spend a lot of compute on this thing, where would that end up? And I think one philosophical reason I can give you is the Bitter lesson, which is, and I think I just posted it or like wrote it here. So the Bitter lesson says the biggest lesson from AI research, last 70 years of AI research, is that methods that leverage computation are ultimately the most effective and by a large margin. And then I think in the same essay, it certainly goes on to say, the methods that seem to scale arbitrarily in this way are search and learning. So this is just one philosophical way of thinking about, why do I even care about scaling? Because it is saying that I want to basically get some methods that if I have more compute, I can do better. And a follow-up to that is, more compute is usually available. So if you look at the history of compute, basically, we are 10xing the amount of compute we have available every like 5 years. What does this mean? So you can imagine that tomorrow, there will be maybe 10 times more compute you have in like a few years for the same cost. So if a method works really well, but does not scale up as well with compute, that method is going to lose out, because you will have a lot more compute. So we are operating in a different regime. You shouldn't think of, what method works best for the compute I have today. I want to really ask the question of what method would keep working best. So let's say in a few years, because I do know this landscape is going to change. But what it means is also that we do need these scalable methods that can leverage better computation. Hopefully this point makes sense, people. And I guess another way, and this is like my interpretation of it, and I like this slide from this person quite a bit, which is you can think about compute on an x-axis. And now, depending on where you are on this axis, the best method would change. It's possible you have a very small amount of compute, and a method might look really good at that scale. So let's say this. But as you spend more and more compute, maybe the other method might work better. So this is also, sorry, go on, yeah?
Go ahead.
So one thing you can think about is like how much inductive biases you're putting in these methods. For example, you can think of even LLMs as one specific instantiation of how to use the internet data. Maybe there are much better ways of using that internet data, and that would even fit here. So basically, this is to say, we are always thinking about, and there's always a point at which we care about. Let's say we might have compute worth, I don't know, 100 million, but we may not have the compute worth 10 billion. So you wouldn't be optimizing for 10 billion worth of compute, because you may not even have it in a few years, or you might run out of money before that. So again, this is the axis you should be thinking about, that you should think of compute versus performance plot. Yeah.
Do you have examples of methods that have been used in AI or ML that do not scale with compute?
Yeah, like think about all the stuff that we were doing pre-LLMs, for example. There was a different training model or model that we were training for summarization, translation, like every task would get its own method or even thing per se. And these were like working really well until we said, what if we just like have a single model trained on all of these, and that just keeps working as I spend more and more training time on this, as opposed to these bespoke specialized summarize. Like basically this is the kind of thing. These models were really good. Let's say I have a summarizer model. That would be really, really amazing. Or a translation model. Like Google Translate had this thing. Google Translate had something where they had a lot of long list of rules. They had some model, of course, some neural network, but also a long list of rules of what to do when this happens and this happens and this happens. And after the LLM stuff started working really well, eventually they swapped out with that transformer, and that just works much better. So it was still AI, because they're using some models and some rule-based learning on top, and some other things also. I don't know the exact details, but eventually they swapped it out with the better thing once it started working much better, which beat Google Translate, which was 20 years worth of tricks and learnings added into the system. So it was not learning-based, but still AI, because it was basically it was not just a rule-based system. There was still some learned components in there, like a neural network, for example, but may not be the right way of using that. Maybe it was only exclusively trained on translation data versus, let's say, a language model which is trained on all of the internet, and then maybe specialized for translation eventually. Does that make sense?
Yeah, it makes sense. So what you're in the example that you give, what really doesn't scale are the rules or the tricks or the code. Basically, if you have like yes, no, or if else.
Okay, so
conditions,
that's a
that
good
doesn't
point. So I guess,
scale.
for example, think about deep learning 2012, when SVMs were beating basically our neural networks most of the time. And then came this neural network thing that we could train for a lot of compute. SVMs did not take that much compute. They use CPUs, for example. And while for neural nets, we can train them on GPUs. So that was the first time where a method which could leverage more compute started beating these existing methods that were dominant. Both are learning-based machine learning methods, except one can leverage a lot more compute. And this is also, I guess, I think it's not like this. Again, this is an axis or graph. So you can have like the same learning method but different design choice. For example, transformer is a specific architecture we came up with. There were RNNs before that. RNNs are also learning-based, right? But maybe we realized that they don't really have a nice property as transformers on this scale. And that's why all the LLMs are based on transformers rather than, let's say, recurrent neural networks. So that's another example. Two learning-based methods, just different inductive biases of what is in the architecture, and that changes the impact of things. Does that make sense?
Yeah. I mean, for the RNNs, aside from I'm not sure the scale issue was what pushed RNNs to the side, but mostly that they don't handle as well long context as transformers. But yeah, I guess so. What you're saying about the SVM or whatnot.
No, but long context is a recent thing, right? Back in 2019, the context lengths were 1024 something. Like,
yeah, but that was long at the time.
yeah, but that's all this thing. That long at that time was too long for RNNs, and maybe now it's not too long. But again, it was maybe someone ran these experiments and found that maybe again it's also ease of compute scaling. So it's not a black and white picture.
What you said with SVMs kind of makes sense because, for example, if you have like a three-dimensional classifier, it doesn't matter how much compute you put on it, you're never going to reach something very serious as an LLM, right? Like that's probably where.
Yeah, and again, the other point to note is it always depends on the compute level you're at. It's possible some method looks really amazing until you scale up compute by orders of magnitude, and that will take us a long time because we need that much amount of compute also available to us and also available generally in the world.
So you need methods that you haven't exhausted the expressive power of the method. Because as I say, like imagine you have like super basic, like a perceptron or something. It doesn't really matter how much data you throw at it.
Yeah,
you'll never get it.
It's both expressive power and learnability too. So it's a mixture of a bunch of things. But again, all of this should be summarized in this. Like you want something more compute better, like higher number good. That's a good summary of all this. All right, cool. So this is about the better lesson. So now I will actually give you a very short primer on reinforcement learning for LLMs. As I said, it's a very short primer. I did highlight that, so don't expect me to explain in details. But generally, like I guess we're putting these LLMs or agents in some complicated environment. Here I copied this environment about interacting with Slack. Let's say we want to make a really nice Slack bot that basically you can talk to and it can reply to your things and do the tasks that you assign it to it. So you can have a setup where basically the agent has some interface of talking to you or dealing with messages and whatnot. And we have some way of evaluating whether the agent did good or not. And then we can basically set up an end-to-end loop that we put this agent or this LLM in that environment. And then it'll take some actions or it'll produce some text that basically will do some stuff in the environment. And then as long as we have a way to evaluate this is a way to scale or not scale. This is a way to train our model to become better Slack bot. And the Slack bot could be simply as simple as, react to my things with a thumbs up emoji because no one else does, let's say, if that's the thing you're going with. And then all the Slack bot has to do is just find your message, thumbs up, and it'll get a reward of +1 and be like, okay, you did well. So let's say that's the kind of thing. And just a little bit of jargon stuff because RL people sometimes have a different way of saying things than the LLM folks. So a policy in reinforcement learning is equivalent to a language model. The state, you can think of it as the prompt we give the language model. Then the action, where I also use this word actions here, you see this, it's basically the output or the tokens from the language model. And then the state is finally, or I guess the state, you can think of it as whatever the prompt was and the output of the language model or the environment. But it's basically things which have happened so far. But in a lot of simple scenarios, you can think of it as a calculation of just the prompt plus the output. A more simpler version, so this is like complicated stuff. Let's go to a very simple version of this. So let's say we want to solve math problems with language models. This is a very simple R environment. This is the input. The language model can generate a bunch of responses, and we can have a binary reward, basically. that tells the model this is correct or this is not correct, and then we can train a language model to maximize these two words. It's very simple bare bones RL setup. Cool. And all we are doing actually, so RL in one picture summarized would be the model generates some responses, we check which were correct, which were not, and we just train on the good ones. That is actually what the RL law says to do. So it's not that complicated as people make it to be. It's really as simple as generate stuff, train on the good stuff, continue. And just to make this mathematically true, some scary numbers or equations here, but really all you should think about is the objective is maximize this reward function. You're sampling from our language model, and I guess I just showed if you were to expand the expectation, what would it look like? But all we are doing is we want to maximize the reward under the model sampling distribution, and we can do gradient descent on this. Very simple. This is basically what RL is trying to do, and this is what all of RL is. There are details change in like how this RS come up, what does this tau mean, and there's all that stuff. But this is basically RL summarized for you. There's nothing more to RL than this thing. This is where all of us doing RL are doing. And then there's like tons and tons of details of what is this tau, how does this outcome, blah, 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 blah. So anyways, but gradient descent on this objective is reinforcement learning. And if you do a little bit of math, you can basically expand it out. So I said it's expectation under my model or policy of this reward function. And to do expand it out, basically all you get is, okay, let's just write down the integral. Let's do the differentiation. Then we do the log trick. So this is simply the log trick of if I differentiate with respect to theta, I can always write this in this funny way. And now I convert it back to an expectation. And here you go. This is your policy gradient objective, or this is what our training objective is. This is what you're using for training. And it's very simple to understand. You can think of it as next token prediction, except it's weighted by the rewards, which is if I didn't have this term here, this is simply doing next token prediction on the samples of the model, except I'm weighting them by this rewards. And the other thing is the distribution on which I'm training is not the internet output tokens, it's model's own generated output tokens. That's really the only difference between this and let's say any sort of supervised fine tuning or pre-training loss. So again, you're sampling from the model itself and you're weighting the samples based on their goodness, which is described by the reward. This is, so I have a very nice question here. What's the problem with this objective? Assume we have binary rewards. So this is 1, 0. And I guess to make life easy, I can show this flashless image again. So assume we are in this setup and we are doing our RL objective, which is this thing as it says, okay, if your binary rewards are there, it's 1 or 0. What do you think is the issue with this objective? You have definitely heard about it. Yeah.
It doesn't tell you which specific actions or words were more important or like contributed more to the reward.
Yeah, that's good. He's saying basically you can do a really long thing and then let's say I get like a success or failure. It doesn't really like, I don't know what exactly did I do. And this is not the credit assignment problem. So that's one. Are there other problems people can think of? There are lots of problems, but like that's why I want people to think about this because you have heard of it. You might have heard of some jargon words to say, oh, this problem is this. But yeah, think about it. Binary rewards, this is the objective we are training on. And I guess to simplify, let me flash this image again. So what if the rewards are 1 or 0, you'll train on all the good stuff. And then that's about it. What's an issue?
There's the gold start problem that let's say we have a distribution of questions that the model just can never get to the full answer correctly. Then you will never just
that's a great problem. That is why reasoning LLMs didn't happen until 2023. Because if the model is not actually doing some interesting behavior, then we'll never really actually get it magically, right? Because you're sampling from the model. So the model has to produce something interesting once in a while. Okay. What else?
Delay reward, like you have to do the entire like generation and then
Yeah, I think it's very similar to the credit assignment problem, which is you have really long. What else? There's still more.
Distribution collapse because like the distribution can collapse because you just like learning the like you only get rewarded for like the correct answer. And so on like other stuff you're gonna output like less diverse.
I think that's, I'm not sure if that's a limitation in the sense that that is really the objective. You're saying that I want to train the model so that it produces good stuff. And it's possible now there's a side effect of that, oh, it might produce only like very specific kind of good stuff or a lot of good stuff. But that's like the detail there. But in a sense, the objective is to say, oh, produce samples that actually result in high rewards.
So it has high variance because it's just it could be for and only one trajectory you get high reward, and for all others you get really low reward.
Yeah, what do you mean by high variance? Maybe you want to expand, maybe or someone else want to explain what does he mean by high variance? Because I think we hear this word all the time, high variance, but I think people just don't think about it as much as they should. Does someone want to explain when he says high variance, what is the problem? So he said like, oh, some trajectories get 1 reward while others get 0, and that's high variance. Why would that be a problem? Someone else. Yeah.
So it might just stereotype the output towards the success strategy.
So-
they just over like rigidify their answers to the correct. And they lose the diversity or
No, so that's very similar to the thing, but I think I was discussing what when he said like this is a high variance issue. What is the issue exactly? Yeah.
I'm not sure if this is exactly the same thing, but from a like learning efficiency perspective, if most of the 95% of your runs get 0 reward, then they're not contributing to training at all. So
Yes.
you would ideally, in an ideal world, you'd want every single sample to contribute in some meaningful way.
Yeah, that's good. That still doesn't precisely point to high variance, but it's very related to the point that it is very inefficient in using these samples. Yeah.
So what do you do when you've got an unclear target? Like if you have math, maybe that's not a big problem because you have an objective target where it's like it's correct or it's not correct. But for most language tasks, especially if you're dealing with human jobs, anything cultural, you can't assign a hard 1 and a hard 0 to everything, and you can't put like a hard line.
Yeah, that's not a problem with this objective. That's a problem with the field of RL. That's saying how do you come up with this reward function, or who gives you this numerical reward function which tells you this is how good it is.
But
So-
it's worse if you have a binary reward.
It's both, but I guess I will come to that point later. Yeah.
You say that it makes like the training kind of noisy.
Yeah, that's getting to the high variance a bit, which is basically, let's go back to this image. And there's a bunch of really, really nice point people said. So let's say you're getting some correct, some incorrect. So one thing someone said was, oh, what if our 90% or 95% of these things are incorrect? We're just throwing them away. So that's a problem. The other thing is, let's say if we redraw these things, which is basically I got lucky and I got maybe a couple of correct things. That's nice. But let's say if I redraw the thing, I will not get any correct samples, and I'll just throw away the entire example. So depending on your samples, you're changing the gradient quite a bit. And that's a problem because it really depends on your luck of what you sampled. And that is the thing which introduces high variance, which is it really depends on what you end up sampling. If you were to draw, let's say, a gazillion samples, you will get a really good distribution, right? But we never are sampling gazillion things. We're only sampling like a few things. And then we are estimating this estimator. So think of this mathematically as simply as this is like an estimator where it says sample from my model and then compute this quantity, which is an expectation. You can draw n samples. If you were to draw, let's say, huge amount of samples, this is totally fine. But you always are drawing a very small finite number of samples. So this results in the variance because depending on the samples you draw, your estimator might look very, very different. So literally just do that math of what would be the variance of this thing, and that will show up. So a very simple trick people do is they introduce this thing called baseline, which is almost always the average reward. So what they do is, let's say if you got a bunch of correct samples, a bunch of incorrect samples, you compute the average reward and you just subtract that. So one nice feature of this is now for correct answers, you are actually increasing the probability of those samples, and for incorrect answers, you're decreasing the probability. This does help decrease variance. Again, you have to do some math to actually show that, but intuitively, it helps the issue of, oh, you're not throwing away the samples that did not result in incorrect things, right? You're still training on them. And for the variance stuff, you still have to do some math. And the other thing I would say is this quantity, this R minus average reward, is called the advantage, which you'll see a lot in the later slides. I just wanted to make a point about notation that people use. But again, it's the same objective. And one good fun problem for people is, why is it the same objective as the previous one? That is something they teach in 101 RL classes, but you should actually take the time to say, convince yourself that this objective is exactly the same as this one. Because I did some funky trick. I said, I will add this additional term, subtract it, and I'm saying this is exactly the same thing. And again, note that the expectation term is still there. I'm not saying it's the same thing on finite number of samples. The same thing if I were to draw, this means if you were to draw a gazillion samples. So there is some fun math to be there, but yeah, please keep that in mind. Anyways, this does explain basically the core of the RL stack that we are training our models with. This is the underlying core thing. And then there's a lot of details. I'll go over some of them in the talk today. But hopefully people understand this part so far. Any questions?
So this here, is it common to use the negative samples? So here, from I understand, like you could use negative samples from this equation, because you get zero, and then there is maybe an average reward that's better.
Yeah. So you actually do push down negative samples. This is the default.
So
you always push down the negative samples, because otherwise it's only training on the good samples. And there are different variations. I think each of this is a good design choice to study that. What if you still compute the advantage, but throw away the negative samples? That is a different method. Like if you basically tweak one signal in this equation, you'll get a new method. And there is an archive paper you can find for that method, I guess.
But if you have sampled most of the times negative ones that lead to zero reward, wouldn't this equation just get biased to or? So I am in the, like GRQ or those things. Do they use negative samples? This is what I'm trying to figure out.
Yeah, they do use negative samples. Yes, so RL training is one place where we are maximizing log likelihood of good stuff. Here we are saying, oh, minimize log likelihood of bad stuff. That's maybe one place where RL start to differ, and it's really just a sign thing again. Anyways, this will come up again, so I guess we'll discuss that. Okay. And basically, the result, which at least was in a public technical report, was that if you do reinforcement learning training, it can enable the system scaling, meaning the length of the sequence, this is average length per response, that goes up, meaning it's doing some interesting stuff like error correction, trying out multiple strategies, yada, yada, yada. So that is just like to say that if you do this for a large enough model and do it well, actually you can see some interesting behavior emerge. Again, to be sure, the initial model was probably doing some of it, but not as much. And then reinforcement learning actually basically you can think of it as amplified it. So maybe the model was doing error correction, maybe it was trying some strategies. The chaining behavior maybe came from this thing. That reinforcement learning forced the model to do more of that kind of stuff. All right. Okay, so now I'll be switching gears to this framework for RL scaling. So I guess pre-training had very nice scaling laws. And what does that mean is, basically, you can relate the downstream loss on some test set using this power law, which is C's compute here. And you can see that it actually keeps going down. So this is a scaling law for basically running this shit ton of experiments. And then you find out that actually, if you set all the hyperparameters correctly, that is a thing, then your loss actually is a predictable function of this compute, which is depending on how much compute you have, you can basically find that how does the loss scale. And you can see that it is this power law that it is of this form where more compute will lead to a better loss on the test set. This is amazing, right? Because it can let me predict this downstream test loss based on how much compute I'm willing to spend. And this is always improving. So what does it let me do? It lets me do things like this. So this is from the GPT-4 report where they said, oh, we fit our power law up to compute of this magnitude, and then we extrapolate it. And our prediction actually nearly matched the thing we trained. So basically, before spending your $100 billion, you can spend $100 million, get some high confidence estimate of where you'll end up, and then actually spend your $100 billion. And that's great. This makes basically spending compute a predictable game and not gambling. Because otherwise it'd be crazy, right? You said, oh, I don't know if it's going to work or not. Let me just burn this much money and do it. That is insane. That wouldn't have ever happened. So this is what it gives you, that you can extrapolate. And this is a scaling law. Like it actually is something that is consistently found to be true. Your constants might be different and whatnot, but it is something that is generally true when we're training these language models, just because the architectures are so similar and the data sets are similarly large as the internet and whatnot. Might be a lot of reasons worth thinking about them, that why do we get this form usually. But anyways, this is the reason we care about these scaling laws. And now, what do you think about scaling RL training? And the thing is, pre-training was nice. We have all of the internet, and then we train with next token prediction objective. RL is more wacky because there's a lot of things going on. you have so many algorithms, like I guess you can keep going with the name of, like basically switch out all these alphabets here, and there is a new method paper out there. So it is crazy. And then even in these methods, there's so many design choices that you can change or tweak. And finally, I think the thing is, if I go back to the better lesson slide again, I guess quickly, let me just scroll here. We are running into kind of this issue. Let's say we have some compute and we run RL and we find that this method is better. Can we really say that if I were to scale up compute 10x, is this going to still be better? We don't know because we don't have a way to predict the scaling, right? So this is another issue we are running. And the funny thing is, I guess I showed you this slide of, okay, the RL compute is exploding or increasing. So people are definitely doing this. But how are they doing this? Because are they just gambling or are they actually doing something interesting behind the curtains? Again, I don't know the answer to this. It could be either, but we need a way so that we cannot gamble and possibly do something like this, because this definitely would be too insane to gamble. All right, so let me go back to that slide again. Yeah, so basically, and I guess I was kind of explaining why does this matter. So it's basically nice for researchers because we can run low compute runs and try to predict what would happen in an expensive compute run. Similar reasons for practitioners, and for the field, it becomes more like a science rather than art. That rather than having, oh, you do this design choice, do DAPO, do this thing, do additional thing, do this trick. Rather than that, you can actually have a study of, okay, what works and what not, what scales, what not, and based on that, come up with some recipe. So it starts getting towards the science of similar, like if it'll be crazy if in pre-training they said, oh, my method works, you should use it, and then the $100 billion run is using that thing, and it doesn't work. Like that is not what happens there, right? Similarly, I'm making a case that if you're scaling RL compute so much, we should be thinking about scaling in similar way to pre-training. That is there some sort of predictability we can get? Is there some sort of extrapolation we can get? And this is that talk, or this is going to talk about this. I guess I'm not going to talk too much about the setup. You can read the paper if you're really interested. But basically, long story short, we found something like this as the scaling for RL. This is a sigmoidal curve, and it is more complicated than the power law I was talking about. I'll explain what this means. But first of all, this looks more like a saturating law or sigmoid-like, if you see. And there are a bunch of reasons for this. One simple one, we are fitting something bounded. Like our accuracy can at most be 100%. It cannot be a power law throughout, right? Because it has to actually plateau. You can't surpass 100%. And while the pre-training laws would always say that things will keep increasing or improving as we spend more compute, but there is an upper bound here. The other thing you will see is there are much more terms. So pre-training had just an alpha coefficient, which is if you spend compute, how quickly or basically how steep is the loss decrease with that compute. There is that term there that corresponds to B, which is the scaling curve of exponent B controls steepness. But there is other terms you see also. You see this thing called C mid, and you also see this another thing called A. I actually think the A term is very interesting. It's saying if you were to spend infinite compute, so actually let me describe that. So what does A, B, and C mean? A means what is the ceiling of this scaling, which is if you were to spend infinite compute, or if you had it, where would you land up? And it is saying that you land up at the asymptotic performance A. B is talking about compute efficiency, which is how fast are you going to reach that A point. So if your B value is higher, or this compute efficiency coefficient is higher, then you'll reach to that A point much faster. So this is needed, for example, if I only have so much compute, and maybe I have a more scalable method, but to reach that performance, I need 100x more compute. Maybe I'll use a less scalable one because it fits better for the compute needs. And I think I'll discuss that later. And then CMIT is this interesting thing of basically when does your curve start saturating? Again, this is not a law. Like this is just a scaling curve fit of if I were to run training. So I guess you'll see these funny points of, let's say we run training for these star points, the red star points. Can we extrapolate from there what would happen to this run? And this is saying that, oh, actually, we can find some predictable scaling for the typical, some assumptions. But this kind of predictable scaling is nice that I can run training for some amount of compute and then extrapolate based on this. Yeah.
So when you meant compute here, again, there are two things, right? One is just the rollout, and the other one is the grid and the update.
Okay, that's a great question. So compute in RL, in pre-training, it was very nice. Compute just meant training compute because your data is fixed. You have all of it. In RL, compute means you're spending compute on two things. You are generating samples from the model. So let me go back to the slide. Yeah, so you're generally computing two things. You're sampling from the model. This is also use of compute. This is inference compute. And you're training the model. That's training compute. And when I talk about compute here, it means GPU hours, which is total amount of compute. So it is basically accounting for, and I guess the funny thing in RL is that inference compute can be actually a large amount of compute, much more substantial than training, because you're spending so much time, let's say, sampling. I don't know, think about sampling a sequence which spans, I don't know, 1 million tokens. That's got to be slow, right? Now imagine doing this like 100 times or something. So that is a substantial amount of compute. So here, whenever I say compute, I'm thinking of GPU hours, or total amount of GPU compute here. Cool. So let's just understanding what does this mean. So if you think about this A thingy, basically, this is simply as simple as like the higher asymptote, which is if I were to give this method infinite amount of compute, where this would land up, that's the coefficient A, or asymptote ceiling. Similarly, the B thing is compute efficiency, which is how fast would I reach the asymptote performance. So here you can see that basically both of them have the same asymptotic performance, but the green curve reaches it much faster. Meaning if I have only this much compute, I rather would spend it on the green curve, because I know I can basically get faster returns to my compute spend. Because this is, in a sense, this is proportionate to money, which is how many GPU hours we are willing to spend on it. And this is directly proportional to how much money we are willing to spend on this RL. So it is a curve showing money to performance, sort of. Please, so far so good. And I'll flash this curve. So again, this is a sigmoid-like shape. Simple reason being the metric we are fitting is fast rate or accuracy that is bounded. The other thing is we have a finite task distribution. It's also the other thing you'll see is this is performance on the basically a validation set or in distribution performance. It's not like pre-train. Pre-training you train on internet and you get a scaling curve on everything. Here, the scaling or this performance measurement is on some in distribution set of tasks, because it's really highly going to be a property of what is your training distribution. If I only train on math problems, do we expect it to improve on some really crazy capability out there like the Slack bot agent? Probably not. So you shouldn't be measuring it on that. So again, this is the other difference. And then finally, I think this one you probably know that there are so many design choices interacting in RL that basically you have to. So that's why you get something like that's why. So you should think about in pre-training, the A term did not exist, or this term did not even exist. Basically, everyone would, if you spend more and more compute, everyone would end up at the same asymptote. While here, there is a difference. Actually, depending on the design choices and the method you're picking, you might get a different asymptote, which is very interesting. This is already different from pre-training. So it matters what algorithm and what kind of design choices you're making, because that might be suboptimal if you keep doing that in the longer term or with more compute. Okay, and just to give you an example, a real example of this. So we tried a bunch of recipes from these large training model reports or whatnot. So here, x-axis is showing GPU hours on a log scale. Y-axis says log scale, it is log, but it looks nearly linear. So just believe it is linear because the points are basically linear-like. And it is showing the differences in scaling behavior. This is, again, much more smaller than what typical frontier models would use, but still it's very representative in terms of what happens within this. If you were to, let's say, use whatever DeepSeek folks used, then you'll end up with something like this. And you see it saturates much earlier, and it has lower efficiency. And if you switch to, let's say, methods from these other reports, let's say, Minimax and Magistral. I guess Minimax and Magistral are more interesting ones, right? If you had only like this much compute, you would say that the green guy, Magistral, is much better than Minimax. If you only had, let's say, 2.5K GPU hours or 2,500 GPU hours. But if you actually run them long enough, you'll find that that's not true. And this is the kind of thing that maybe scaling can help you with, or predictability can help you with. That you can run them for some amount of time and then start predicting where they would end up saturating. So that is like the entire hope of why I do the scaling business in the first place. And then the other thing I would say is, I was talking about this, right? Different methods could have different ceilings, and you already see that. Like you see the final performance of these with a lot of compute. They are saturating at different points. They are not saturating all at the same point. Like two of them are. These two guys are saturating at very similar points, and you see a difference in compute efficiency that this learns much faster. But if you had enough compute, both of them would end up reaching the same point. So then you think about other things like how stable or robust this method is this too annoying to tune hyperparameters and a bunch of other things. Like all these things come into play when you're faced with something like this. But other than that, usually you go with something that has higher compute scale. Like I'll always prefer this minimax method over other methods if I knew I have compute more than, let's say, 16 kg/h or something.
In scalar from this paper.
Yeah, scalar is a hodgepodge. So scalar does not invent any new thing. It just combines a lot of these existing design choices, studies them, and I'll discuss what the scalar is, and then just shows that you can do much better from basically than these recipes basically. But yeah, it is like think of it as a hodgepodge of existing things rather than a new method, which just says if I were to study scaling of all these things and then to combine them, this is what I end up getting. Again, this is my gentle reminder or better lesson again. So, and maybe this, sorry, yeah.
So yes, you talk about the better lesson, but like with those results, it seems that like this kind of miss out, like not in the right, like it doesn't fit real well with the bitter lesson narrative, because if you think about like typically what the bitter lesson applies to, it's like playing Go or like chess or like scaling stuff that kind of like don't have like a cap on it. You know, you can become arbitrarily good at Go, you can become arbitrarily good at math. But if for every time you need to like set up an RL environment and then it's like maxed out by like your like the environment you have built or like
wait, Go is an RL environment. Sorry.
yes.
So
It's like one in which you can become like arbitrarily good.
you can, right?
never
Maybe
really
it's a
stop.
limit of our methods. It's possible. The highest performance is 100%. That is also the same in Go. Highest performance is you just beat everything around you. It's just a limitation of like this depends a lot on the model you're training on, how much time you trained it for, the exact method you use. I'm not saying that this is like nobody's saying 60% is the max you can get, right? There is probably a better model and method out there that can do this. So bitter lesson all just says we want things that scale better with compute.
Yeah, I was gonna say something along the same lines. Like it seems like A is the problem here. Like if you could just get A to be as high as possible. Then,
Yeah. So you
then you're
want
good. Yeah,
if-
but if you wanted a proper scale, like if you wanted a scaling law, like
Yeah,
capital
so-
scaling law, you want to find out how A relates to other.
Yeah, so that's what I'm saying. This is not a scaling law.
Yeah,
This
yeah.
is a scaling fit.
No, but it's a cool observation.
I was just saying also for the Go thing, maybe the difference could be that right now we're not considering a process reward. Like when you want to get arbitrarily good, maybe you would also want to consider how fast are you beating someone, how well are you beating them.
Yeah. So there's a lot of, again, as I said, there's so many design choices that go into that. And all of these can shift, let's say, this curve. Like this is just saying, this is an observational thing that if we were to run RL with certain setups, this is what we find most of the time. And now the question becomes, is there a way to push this A thing or B thing? If this is generally true, again, there is a big if there. It's possible this may not hold if you switch setups quite a bit, because this is a very like new thing, right? People were not studying RL scaling in this way before this. Yeah.
Also, bitter lesson comments on it doesn't really make sense to like plot all this, to do all this on one task. Like maybe there's a method that would be very slow here, but actually, like if you train it to 100 tasks, like 1,000 tasks at the same time, it would beat the others.
That's a good point. That's a very different kind of compute scaling. I would say it still makes sense. The Go was a single task, and basically, bitter lesson can be applied to like again, this is in distribution performance. I am saying if I give you infinite math problems to train on and infinite compute, what do you expect to happen? And you can still think of it as a very simplified environment. Math problems have a lot of diversity too, but you're right. Maybe the way to interpret your comment is if I mixed in a lot of different tasks, it's possible that might again change these things, and the rankings might differ suddenly again, which is true. Like this is so basically we will study this kind of setup in the setting we care about, which is let's say in the typical language model setting, we care about a lot of multiple tasks. So we would study this behavior there, and there are some results which I wouldn't discuss here, but yeah, that's exactly. Cool. Yeah.
Just another point on the A thing. Like technically on a lot of these math type problems, we should be hitting 100% in the asymptotic case.
Some problems are really hard, I guess, which just the model never learns to solve is the way you can think about it. Like think about, I don't know, if I told you prove P equal to NP. That's a math problem. Basically, we'll never solve it. So there might be certain problems that are like, it depends on the model size too, right? Like if I were to use a much bigger model, it's possible that we hit close to 99, but there are still problems like the P equal to NP case that you just might never solve. So it all depends on how good your model is and what was the data you trained on. So this is all a complicated function of that. And that's why the saturation, like again, if you were to just look at these three things, you might think, oh, maximum performance is 50%, but unless you see that other method and you realize, oh, actually, I can do much better. So, and I'm guessing there might be much better things than this too. Like someone mentioned process rewards, that could be a way to lift this. I don't know, like that someone should study that. Yeah.
So the scaling law that you showed for
Scaling
reward,
fit,
the
not
scaling,
law.
the previous one was the.
So this is,
You call it scaling fit, or this is scaling sheet. And then the next one here, do you have a fit or something?
so this is, that's the thing. These are real points, and then the cross are extrapolation. So it shows basically these are our training points, and these are extended training points. We did train, but we didn't fit our scaling thing there, and we are extrapolating. That's what the dotted line is saying, and we're just showing that the extrapolation kind of aligns with where we would end up.
No.
But again, this is not a law. This is just a fit to predict. If you have to cover our bases. That's what we do for conferences.
But again, how did you fit? So
you actually like basically, yeah, that's a
you
great
get the
question.
reward, right? So here
So
you see the reward.
So this is the equation. You have
Right.
parameters A. Yeah, that's a great question. How do we fit the scaling thing, right? I keep talking about this is the scaling fit. So we actually observe the rewards, which is the R values at these points.
Yeah.
We can assume that equation is
Yes.
true,
Okay.
and then we can fit,
Yeah. this one
minimize
you fit.
the error, and then that's how you fit it on the observed data, all these star points. And then you can just extrapolate, because once you find A and B and C.
Yeah, I get that. Like now, how did you go from R to the pass rate?
Oh, I
This
guess
one
for
gives you-
binary problems, it's for binary rewards, R and pass rates, average reward is same as pass
Oh,
rate.
okay, so I see this.
It's like, that's why I just like, this is supposed to be expected reward. So this is
Okay.
always true for any reward function. Again, I am saying that, but we only studied it for binary rewards. So someone has to check that if the rewards are continuous, we still get something like this. Yeah.
So what's missing for this to be a law? Like what would you have to do more?
So I guess that's a great question. You should ask, how do we build a law in pre-training? So pre-training basically takes any compute, for any amount of compute, you do all possible things or all possible hyperparameter stuff and find the best thing. So you see all these blue lines? They're basically running lots and lots of things at that compute. Like these are ISO compute curves. And then you're finding the best thing and you're putting that one. So this is like basically the optimal loss scaling. It's basically, these are all fits. These all could be fits or whatever. But like for the law, you actually have to show that for this amount of compute, this is the best possible thing I can get. And you actually have to try out all sort of, so these lines you might get from different hyperparameter settings like dataset sizes, for example, and then how many epochs you do, or what was your atom optimizer and stuff like that. So there are a lot of different ways to get this. But to make it a law, you actually have to spend a lot more compute for each point on that plot and ensure that, oh, this is what I get. Yeah, that was a good question. All right. I am running short on time, but I will try. Cool. So I guess I was saying this. So basically, this is one lesson I want to drive home that, oh, the best method at 5K GPU hours is not the best at 100 hours necessarily. That is something that you can actually gain. Let's say, so this is the point I was making, that once you put these scaling things, you can actually check what would happen if I were to extrapolate my compute and based on that decide, rather than just using the ranking. Like if you were to go back to this plot, sorry, not this one, you will see again, if I were to decide based on just like ranking here, I would have picked the green thing, but green is suboptimal. And this can happen a lot in real world. I will give you more examples later. The other nice thing we did was, so this was a project where we did have a lot of compute somehow. And we did spend a lot of it. So we ran like a single 100K GPU hour runs. That would cost you about $1 million, I think. So basically, we did see that, oh, this thing actually fits there. And we tried a bigger model sizes and whatnot. And you can see here again, we followed the same principle as we trained on some points. We fit this thing, and then we predict where would this end up. I think for the yellow curve, we trained for 16K hours, and then we extrapolated to 50K. So like 3x extrapolation. And this still generally holds, is what the message here is. But we could predict, basically. The other nice thing I want to show is, the only difference here in these two curves is the model size. And you can see if I switch to a bigger model, it leads to a higher asymptote and also higher efficiency. Just looking at the slope of these guys, I think. Not sure about the efficiency, but it definitely leads to a higher asymptote, which means, so imagine this is like, again, a very small model relative to the frontier models we use. This is 17B cross 16, like 100 billion parameters. We use actually way bigger models. And things like that do impact the scaling. With the same task, same method, everything same, except I change the model size of what I'm training. And that will change what these coefficients would look like and what kind of scaling do we expect. Yeah.
So what is not allowing this classic RL that we know if we increase the size of model RL usually?
So the classic RL typically is not in the regimes of billions of parameters. And there's also this big stage of pre-training that we typically don't do. So the model size is increased, but it was also trained on all of internet. So it absorbed more of it in some sense. So you can think of it as like we say, right? People used to say that, oh, this model seems more smarter after pre-training than this other model, even though they're trained on the same data. It's just that there is a notion of, oh, maybe you actually squeezed out more knowledge or generalized a bit more in some sense. So that is also happening here. If in RL we were doing that, it's possible we'll see that sort of thing. It's just that we need to do pre-training like thing. Yeah.
So like RL scaling region, what you would actually be interested in would be like to fit like some scaling law, but for like or as you scale the model size, how like the limit.
So you would have a ladder of models, like how people do things in pre-training. You have a ladder of model sizes, and you will fit where the performance lands up for some amount of compute. And then based on that, decide what would be the next model size and stuff like that. You have already done this in pre-training, but yeah, basically you need to try different things. And then based on that, try to predict where you would end up. Like basically these are, if I go to the GPT for stuff again, these are different model sizes, right? It's the same data. So they just are predicting at different compute scales. This is where they end up. And then they say, oh, if I extrapolate, this is where I would be. So let's just do that.
So you guys also
we did not do that. We already burnt a lot of money on this. But yeah, that is a good follow-up work for this sort of thing. That would become a scaling law, yes. So that will become a proper scaling law, assuming this framework holds.
Because at this point, you always need some runs for you, and then you can extrapolate.
Yeah, so here, for example, what you would do is you would actually fit, like basically have some compute scale, and you will basically fit the point, and you get a lot of these points like for different compute scales. This is the best you can get, and then you can extrapolate that, and then you can switch compute with model size, for example.
Yeah.
Or you can ablate things with that to like you have, basically a lot of things you can do with this. This is just the start. All right. So what have we learned so far? We have learned that RL training curves usually follow in sigmoidal patterns, not forward laws. Different recipes can have different asymptotic performance. And we can sort of predict large scale performance from smaller runs. Yeah.
How did you come up with the equation?
That's a great point. It came up in a dream, but we tried so the thing is we tried power law first, and it did not give us very good extrapolation. And then usually when we look at the shape of these things, something like this makes sense. So it's a sigmoidal thing. The funny thing is this is actually a very common form of scaling. It's also used in like medical domains and whatnot to predict the concentration of a drug. So, but it's a great question. Like, is this the best fit? I think that's an unanswered one. We just found this was much better than the power law that people usually fit.
Mostly empirical.
Yeah, it's mostly empirical. There might be better fits, and when do I say a fit would be better or not? If it gives you higher extrapolation ability, that is a better fit. I don't like fitting the data is one thing, but predicting the future is the other thing. And really, what I want is this ability to predict this really well. The other thing could be how more of an extrapolation can I do? Like here, for example, I think some hunches that you have to run until CMID to actually get a good fit. But is there something that I can maybe run right until there or just before it and still actually have the ability to predict? So again, this is empirical, is the short answer. It is a common form, but there might be better forms out there. If someone is very interested in studying, should just reach out to the first author, get all the data if he can send you. And then it's a math task of, okay, can we predict better scaling here? Yeah.
With this law, with this fit function, do you have to, how far along the curve of expected data do you have to go?
Yeah, that's what I'm saying. So I think just because of the form of this law, you actually have to run CMID at least, and then it's slightly bit more would give you. But that's the thing, right? We don't know this a priori either. So it's like not an easy problem. Generally, we extrapolated like 2 to 3x for most of the plots. So like we ran for 8K and we can predict 16K or 24K. So that, but ideally, maybe we want to run even smaller and then extrapolate more. Okay, I will continue. 6 minutes. I do have a lot more slides, so I will zoom through them. No questions for the next 5 minutes. But yeah, just to give you some idea of what were the components in the scale-RL recipe, I wanted to cover some of these, but they were basically a bunch of these things. I don't want to spend too much time here. Yeah, let's just talk about this. I think it's fine to cover some of the
We
slides.
covered some of this in the previous.
Yeah. So I think last lecture, Dima talked about something like this. So one thing, for example, we do for language models is I gave you a very simple picture, I gave you the loss, I gave you very nice equations, but actual training also cares about efficiency, right? So what happens is you can do this thing called on-policy RL or synchronous. You generate, you train, you generate, you train, right? But this has a lot of idle GPUs. You're wasting a lot of your compute waiting for this training step to happen. So basically, you generate, let's say this generation finished. You're just now waiting for the longest generation to finish. So there is a lot of wastage of compute here. That is not what we typically do in practice. What we typically do is something like this, which is we overlap the generation and training. So you generate one batch, then you start generating another, and then you train on the first batch. This is the overlap. Yeah.
If you're short on time, you might consider skipping this one because Dimitri was here 2 weeks ago explaining pipeline around.
Yes. So basically, if you guys understand this, I will basically I'll just show up this. So there are two ways of doing off-policy RL. One is simply you do this thing of overlapping stuff. The other is the crazy thing which pipeline RL does, that it says, let's just if you guys assuming you understand pipeline RL, that's the other comparison. And then we just studied, well, what does scale better? And the thing we found was both of them actually scale equally well in terms of asymptote, but pipeline RL has much higher efficiency. So basically I can get the same results. And let's say, think about 2K GPU hours. I already get the same result if I were to run the other conventional thing for much longer. So this is a very good way to win compute efficiency. And this kind of aligns with the expectations, right? Like we did all that thing to make things more efficient. And it turns out that, yes, indeed, it does make more efficient. But the nice thing is it doesn't degrade the asymptote. Everything was there exactly matched. Yeah, I'll skip this. Let me skip this too. This is not as interesting. So many go. Okay, I'll talk about the second topic. So this is maybe one of the biggest issues we have in basically training our frontier language models, which is this thing called train inference discrepancy. And what is this? We are sampling from the model and we are training the model. You would think they're the same thing. They're not. There's a sampling engine. This is your VLM, HLM, whatever. And there's a training engine, let's say Neutron, whatever. But sampler and trainer are different things. And they're optimized for different things. Samplers are optimized to be really fast. Trainers are optimized to train a lot of data quickly. Very different stuff, very different kernels. So if you take the same model weights and just roll out and compute the probabilities of what, let's say, the sampler gives it. So I generate some samples, compute the log probabilities of what the model gives me. Similarly, I just pass these samples to the trainer and say, hey, what are the log probabilities of these things? You get this magical plot like this. You expect this to be aligned. You expect this to be y equal to x line, but that's never happened. For any big enough model and any practical setup, you always have something like this, which is there is a discrepancy between trainer and what it means is like we change the RL objective under the hood, which is I said, oh, we are sampling from the exact model, but no, we are actually sampling from this guy. And this is a different objective than what we were training, or at least we asked for training, right? And then there are like there are like both algorithmic level fixes for this and like systems level fixes for this. So let me just quickly flash the algorithm level fix. Let's say, yeah, so this is the algorithmic level fix. You can just, basically you can trust me here, this objective, the one above, is exactly the same as I presented earlier, because I added a correction down here that I should divide by the samples probability or whatnot. So this is basically saying, at least let's just optimize the same exact objective that we promised or we said what RL is doing. That's one kind of fix. And the other kind of fix is something like this. So this is from some report which trained a trillion parameter language model. And all they're doing is they keep the same RL algorithm and everything else fixed. They are just finding all these discrepancies and then fixing them one by one. So basically every discrepancy fix might delay or degrade your speed, because you are actually like this thing was optimized for inference, but you're saying, no, 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 I want something to match with trainer, so that you're basically getting higher precision or higher alignment with the trainer, but there might be a trade-off. But all they're showing here is very funny thing. But this is where they started. Like they start making all these fixes in different components of the transformer architecture. They get that beautiful red curve. And this kind of thing is like pretty bad because it's a silent killer. All it does is there's no error. Our training runs fine and whatnot. Suddenly we just see this kind of thing, that the training curve collapses. So imagine now you're running your, I don't know, $100 billion run, and suddenly after like, I don't know, a month, this happens. So you don't want that to happen. And this is like a big problem with the thing. And the bigger your models and the more complicated pieces in your model, the more likely something like this would happen.
But even this is not guaranteed, right? You don't know whether it will fall.
Yeah, it is basically very much a function of the system and the model we are at. And for each, the fixes that work for your model may not even work for someone else's model. And very much dependent on the training and inference libraries, like exactly the infra you're using. But this is just a very provocative example of there is no change in method here. And this is what it gives you. And like in our experiments too, we tried one simple fix from these guys, Minimax, where they said you could do the final matrix multiplication in NP32. So just change one operation to be higher, like higher precision. You actually go from something like this to this. And then if you actually plot the scaling curves, this was one of the biggest impacts we saw on scaling. Like just fixing this, we can do all the algorithmic fixes, we can do a bunch of stuff, but if you just change this, and this is very specific to this model and this setup, and it also works for these guys, it may not work for other guys. Again, that's another thing, because as I said, it depends highly on the infra that you're using and the libraries you're using to the level of the kernels you're using, like what version of CUDA did you install? That would change this thing. So this is like, if you were to go in a systems mindset, you will say, I will do something like this, find all the pain points and fix it. And then you need a lot of, that's one viewpoint. The other viewpoint could be, well, this is unavoidable. Maybe let's just try to fix it algorithmically. So that's like a very active area of research in the field, that how do we actually avoid these kind of issues because they happen. Let me just present one more slide. So I guess, yeah, jumping to this slide again. I will share the slides, but basically all I wanted to do was, let's say people are telling you that, oh, we want to get here. Now you have some sort of language to talk about what do they really mean and what do you need to do certain things. There are a lot of interesting design choices that I did not cover, but I think the slides have a lot of them and a lot of reading material you can find afterwards. Yeah, I guess now we can take questions if you do have time.
It would be more like real feelings, some part of which you need to impute to the LLM. That could also be instead of just failing values.
Yeah, I think this is, again, this is a very like cartoonish picture of the reality is it is some proportion of pre-training in RL compute. It could go either way. For example, people are trying to figure out how do we do pre-training with RL, for example. And if that happens, then this picture is like inevitable. But then it also depends on, let me show you one plot which is skipped. So, the number of training environments,